Alright, so in this video, what we are going to do is we're going to look at a specific form of sequences or series, which we call arithmetic progressions. Alright, and we'll try to evaluate how to figure out, say, the nth or the m term of an arithmetic progression, because they all share the same property. Okay, so an arithmetic progression would look something like 2, 4, 6, 8, 10, 12, or something like 3, 6, 9, 12, or it could look something like 1, 5, 9, and 13, and you add on, and you get 17. Okay, so what's common in all these series or progressions is the fact that they all have a common difference. So they have a common difference. And what do I mean by common difference? A common difference is the fact that they all, in all these sequences, consecutive numbers differ by a certain value. For example, if you take a look at the first equation, you have 2, 4. And how do you get 4 from 2? You get by adding 2. And 6 and then 4. How do you get 6 from 4? You add 2 again. And similarly, you keep on adding 2, and you get 12, so on and so forth. So the idea behind the sequence is you continuously add 2. Also, you start from 2. Okay, so these are two very important numbers. The fact that first forms the difference, and second forms the first number. Okay, now, similarly, if you look at this series, well, you notice that the first number is 3, and how do you get 6 from 3? You get it by adding 3. Similarly, how do you get 9 from 6? You get that by adding 3 again. And similarly, how do you get 12 from 9? Well, you add 3 to that. So the common difference here is 3, and the common difference there was 2. In this one, well, this is not a table of 2 or 3, this is a slightly different one, but the idea behind this is the same. How do you get 5 from 1? Well, you add 4. How do you get 9 from 5? Well, you add 4 again. How do you get 13 from 9? You add 4. And how do you get 17 from 13? You add 4 again. So the way to represent this number in the sequence would be to take care or to take into account the difference, the common difference, which would be 4, and the fact that one of these numbers. So we can take 1 in that case. So if I know 1 and I know the common difference to be, say, 4, then I basically have all the information for the sequence. I don't need to plot them down or write them down explicitly. All I can do is work with this piece of information: the first letter, first number, and common difference. Okay, so that is the idea behind a arithmetic progression. Alright, so now what we can do is we can write a general sequence that forms our arithmetic progression. Okay, so we call them APs, and we start with a first number, which we call A, and then the second number would be A plus D, if D is the difference, and a third number in that case would be A plus D plus D. So you add D to this, so you get A plus 2D, and you add D to this term, and you get A plus 3D, so on and so forth, and this is how the sequence would go. Now let's talk about the indexing. So if somebody asks me what is the first term of the sequence, I say the first term of the sequence has to be A. Okay, so I call the indexing by, say, n, and I call this A1. Okay, or let's call this some other, well, let's call this I don't know, K1. Okay, so this is K, and this is 1. So I am representing here Kns. Okay, K is the number appearing in my AP. A is the starting number, D is the common difference, and K sub 1 therefore means the first number in the AP. And similarly, this would be K sub 2, and this would be K sub 3, and this would be K sub 4. Okay, so we notice a pattern. If I ask you what is K sub 5, well, you see that if I need 4, I have to add 3D. If I need a 3, well, if I need a 3, then I need to add 2D to A. So what that tells me is that if I need to get 5, I need to add A plus 5 minus 1D. Okay, so keeping this pattern going, if I ask what's K6, then that would be A plus 6 minus 1D. And it doesn't take long to figure out that if I need Kn, the nth number in the AP, then that would be A plus n minus 1D. Okay, so that is how I would represent my AP, my nth term in the AP. Okay, so usually what we do is we can say that we need a first number to start with, and then we need a common difference. And then, given whatever index we choose to evaluate that sequence's number, we basically need to put in that index value, which is given by n, and we get the number of the sequence. So let's take another example. So in the previous cases, we analyzed a particular example, which was something like 1, 5, 9, and then what was next? Well, I think that was 13, then 17, and so on. Now, I don't want to do the math. I know that this is my first number, so this is k sub 1. This is my second number, this is k sub 2, and so on and so forth. This is k sub 3, and this here would be k sub 5. Okay, so we agree on that. So far, so good. So what are the numbers that categorize this AP? So this AP is categorized by the first number and the common difference, which is plus 4. So that tells me if I need to figure out the nth term of the AP, then I must do that. I must take let me write it down in terms of variables for now. A plus n minus 1d. Now from whatever I've analyzed before, I know A is nothing but 1, and D is nothing but plus 4. So this gives me the nth term of this AP would be 1 plus n minus 1 times 4. Now I can solve this a bit more and I can get something like 4n minus 3. So that's because 4 times n is 4n, and then 4 times minus 1 is minus 4, but you add 1, you get minus 3. So this sequence is given by the functional form of 4n minus 3. Okay, so if I was lazy and I didn't want to write all terms of the sequence, and somebody asks me, okay, what is the 12th term of the sequence? Somebody asks me, what is k12? I would reply by using this formula, because k12 would just be 4 times 12 minus 3. And 12 times 4 is, 8, and 4, that's 4, 48, and then we subtract 3, we get 45. So you see, it didn't take long for me to get something k12, and that would be 48. That's pretty good. So that is how these arithmetic progressions are represented. Now, a few pointers here. There's nothing that really stops the difference from being negative. That is to say, we can have a decreasing sequence. For example, we can have something like, let's say, we can have something that goes along the lines of 4, 1, minus 2, minus 5, and minus 8. So what's different about it as well? You clearly see it's decreasing 1 as the index increases. As the index here is 1, 2, 3, 4, and 5. As you see, as you go to a greater index, your numbers keep on decreasing. So you can see that's happening from 4 to 8. What's another thing is that is happening is because your difference here is, it's not 3, it's 1 minus 4, so that's minus 3. Okay, so if I have to write the nth term for this AP, I see it's an AP because the difference here is always minus 3, minus 3, minus 3. Okay, and then I would write it as first term, which is 4, plus n minus 1 times the difference, which is minus 3. So you see what this gives me is 4 minus 3n minus 1. And I can solve this a bit more to get 4 minus 3, so that's 4 plus 3, minus 3n. And that gives me 7 minus 3n. Okay, so this AP is represented by my equation. The functional form is 7 minus 3n. This will go on as big or small you want your index to be. Also, it starts from 4. Alright, so this is how APs can also look like. There's nothing really that's stopping the difference to be negative. It can also be a fraction. It can also be an irrational number. It doesn't really matter. Okay, but the only thing is that n has to be an index. It has to be an integer, and anything else can follow. Okay, so that is how you would get the nth term of an AP, and the equation for that is a plus n minus 1 times d is k sub n. So there you go. Hope this video made sense and hope it's helpful to you, because the next video we're going to take a look at how we evaluate sums of AP, and we're going to use this formula in order to evaluate that. Okay, and later on we're going to move on to geometric progressions, repeat the same thing again, and you will see how things change in case of geometric progressions, and you would also see how to cleverly construct APs if many problems, if a problem statement requires you to do so. So all the very best and have fun.